Oh, hello guys. So we have this question, which is power screws, and is taken from the question paper of the first course of machine design. So basically, the setup of this question in this diagram, we have the motor that will help us with the torque, and then we have some sort of a gearbox, and then we have the collar bearing, we have our lead screw, and then the nut which will move up and down in that lead screw. So we'll be converting some rotational movement into linear movement. Your nut is moving in a linear motion, and then whereas your lead screw is giving us your rotation motion. This is a very important application in mechatronics industry, or maybe also some electrical or whatever. So you can pause the video and read the question and even attempt the question. So I will point out few important aspects. So we have two colors in this question, and since this question is set up in a vertical way, what I mean is our nut is moving up and down, and then your collars will be adding to your load. So we will have to consider both collars in our calculations. So if this setup was given as horizontal, say your nut was moving in a horizontal direction, we were only going to consider one collar, right? I will show you when we're doing the solutions what I mean by that. So after pausing the video, we can look at the proposed solutions, right? So the first question is asking for your maximum load that can be attached to a nut if 2 kilowatts of power is given to the motor, right? So in the information we're given your revolutions per minute, and then if you recall that power is your torque multiplied by your angular velocity, and then your angular velocity must be in radians per second. So the only thing we need to do here is to convert your revs per minute into your radians per second using this formula, and then it works out to 125.7 radians per second. And then from this equation we can calculate our torque, which will work out to 15.9 Newton meters. And then the next thing is to calculate the mean diameter. So the mean diameter, we are given the major diameter, we are given the pitch, so we can calculate the mean diameter, which is the major diameter minus pitch over 2, and it works out to be 50 millimeters. All right, so from Shigley's mechanical design book, we can use equation 8.1 and 8.6 to calculate the torque that will be required to raise the load. So combining the two equations, and you will notice that my 8.6 is different from what you have in your book. The only difference is these two that I'm highlighting. The reason for that too, remember I said we need to consider both collars because our question is, the setup is given in vertically. So if our setup was in this way, we were gonna use that equation as in the book. So now we're combining equation 8.6 and 8.1, and then we have calculated your raising torque from above, and then the only unknown in this equation is your force, which is the required load. in this question. So substituting all the data which is given, and another thing that we need to notice here, for my lead, which is L, I'm using the pitch because they said this is a single thread. So remember, for a single thread, your lead is equal to your pitch, right? So we've answered the first question. The load is 686.98. And then moving to part B of the question, which is asking for the efficiency of the power through. So we need to first calculate the output torque. We can use this equation, which is your load multiplied by your lead over 2 pi, and then your output torque is 0.437 Newton meters, and then your efficiency will just be your output torque over your raising torque, and it works out to be 0.027. Moving to part C of the question, which is asking for the linear speed. Remember that your lead is the distance that the nut moves parallel to the screw axis when the nut is given 110, right? So now we need to convert your revs per minute into revs per second, and then you just multiply by the lead to get your velocity, which works out to be 80 millimeters per second. That's our velocity, linear speed. Yeah. And then the last part of the question has to do with the self-locking feature. Remember, I have a side note here. In order for this setup to be self-locking, the highlighted part in this equation, which is your lowering torque, it needs to be positive. And then, as we can see, like from the maths here, in order for this to be positive, this top part, the pi f dm needs to be greater than your lead. In order, that's just maths. So the condition for self-locking can be given as this, right? And then substituting the given values, we get 15.7. So if our lead if our lead can be greater than that 15.7 millimeters, our setup won't be self-locking. That's what basically is asked on that question, right? Thank you for listening. So I will be uploading more of these videos. If this was helpful, please subscribe for more videos, and you can leave the comment if there's something unclear or you want to correct me for any mistake. Thank you.